Hello, everybody. I hope you are doing well wherever you are. In this lesson, I'm going to introduce you to the fundamentals of all electronic devices. We are going to look at the materials used to make electronic devices before we delve into any sort of circuit analysis or even look at any electronic device. This is going to be a lot of theory, but the theory is vital in understanding many of the electronic devices we will look at. So it's imperative to watch the video if you do not know the material for your own good. Without any further ado, let's get started with the lesson. So guys, what are electronic devices made up of? Electronic devices are made up of semiconductive material, and the most commonly used semiconductors to make electronic devices is silicon and germanium. Germanium. It's silicon and germanium. These are the most widely used semiconductors to make electronic devices. Germanium was mostly used in the past, but nowadays they are using silicon. And silicon is a semiconductor, meaning that it can behave both as an insulator as well as a conductor. So it can allow current to flow through it, and it can also block it. So continuing with the lesson, let's go further. Now we are going to compare the atomic structure of silicon to that of copper. We want to show you what makes copper more conductive than silicon. So what we are going to use the Bohr atomic model. We are going to look at the silicon Bohr model as well as the copper Bohr model, atomic Bohr model. So in front of you, as you can see, we already have these two atoms. We have a silicon atom on the left hand side and a copper atom on the right hand side. As you can see, I'll assume that you already know most of this from your chemistry classes. So as you know, silicon has 4 valence electrons and copper has only 1 valence electron. And the red part is the core. The red part includes the nucleus and all the other orbitals, excluding the valence orbital. So as you can see, the core of silicon is more positive than that of copper. And you know that an electron has a negative charge, and the core, as you can see, for silicon it has a positive 1 charge, and for copper it has a positive 1 charge, and for silicon it has a positive 4 charge. And looking at silicon now, you know that unlike charges attract each other, and same goes to the silicon atom. But in copper, the charge, and you can see the positive charge is not very strong compared to that of silicon. That of silicon is very strong. So the valence electrons of silicon are more strongly attracted to the whole atom than those of copper. So if we were at, you know that copper is a conductor, so it's easy for this electron in copper to become a conduction electron, because it is less strongly attracted to the whole structure, the whole atom. So it can escape this atom so that it conducts, so that it becomes part of the current. It can flow, it can move out of the whole atom, because there's a very weak force that is holding it. So if an external force is applied, that external force will be able to overcome this attraction force because it's very weak, so that this electron becomes a conduction electron. I hope you get that, guys. So with silicon, the core is more positively charged. So all these other electrons are strongly attracted to the atom itself. So it will take more voltage to loosen these electrons from their valence shells so that they become conduction electrons. So in copper, it takes less energy so that electrons can start flowing. But in silicon, it takes more energy in order to start electron flow. Continuing. I've already explained most of this. I've already talked about most of all these points. So you can go through them. If you want to take notes, you can take. We have already gone through most of all these points. What I was explaining is also explained in these points. Now, let's take a look at a silicon crystal. So a silicon crystal is just a solid of silicon, just like we have a copper wire. Now imagine we are looking at a silicon wire or a silicon solid. A silicon crystal is just a 3D arrangement of silicon atoms. As I've already explained, the silicon atoms are not the silicon atoms. Okay, sorry guys, sorry, I'm making a mistake. I'm getting a bit confused. Okay, let's read out this point. It says, silicon atoms are bonded together by covalent bonds, where adjacent atoms share their valence electrons between each other. So you should know this from your chemistry class. I'm not going to go over it. I will assume you know it. Moving on, guys. Now here's a structure, an overview of a silicon crystal. As you can see, the red parts are the cores of each silicon atom, whereas I only want to show the valence shells or the valence orbitals. I don't want to show all the shells. That would take up more space. So that's why I'm only drawing one shell and the core. So as you can see, the valence electrons are all shared between these between these atoms which are adjacent to each other. So these valence electrons of this atom will also jump. Sometimes they might jump to this valence shell of this other atom. So that's what I'm trying to say, guys. So that's what covalent bonding is all about. Sharing of electrons between adjacent atoms. Moving on. Now, let's look, even though I've already explained the flow of current is in silicon, but let's delve in deeper and look at the flow of current in a silicon crystal. Here we are calling this silicon crystal intrinsic, meaning this silicon crystal is a pure silicon crystal with no impurities. So the way a silicon crystal conducts current is vital to the understanding of most electronic devices. The electrons in any material can exist within prescribed energy levels, and these energy levels are the same as the valence, the shells, not the valence shells, but the shells or the orbitals. So these energy levels, so atoms can only exist within electrons. I'm confusing things. Sorry guys, please forgive me. Sometimes I get confused. Okay, moving on. the electrons in any material, as I've already said, can only exist within prescribed energy levels. So these energy levels are visualized to be the shells themselves. So an electron can only exist in an energy level and that can hold the amount of energy it contains. The conduction band. So the conduction band. This is the region where electrons are free to move around, where they could potentially constitute as current or electron flow. Moving on to the next slide. As I've already said, that electrons can only exist within certain energy bands. This one is the valence shell energy band, and we know for a silicon crystal we have 4 electrons. We have 4 electrons in that shell. So, and we know that we have a conduction band where these electrons can jump into and then constitute as a current. But as for now, the silicon electrons are at the valence energy level, meaning they are not in the conduction band. For any silicon crystal which is at 0 Kelvin or absolute 0 temperature, there are no electrons in the conduction band. All the electrons exist in their prescribed orbitals or energy levels. As you can see in front of the screen, we have 2 silicon atoms and we have 2 valence shells. For a silicon atom at a silicon crystal at 0 degrees, not 0 degrees Celsius, because 0 degrees Celsius is not yet absolute 0. At absolute 0 degrees, absolute 0 temperature, there are no electrons in the conduction band. The electrons exist in their prescribed energy levels for a silicon crystal at absolute 0 temperature. So let's look at what happens if we raise the temperature of the silicon crystal at any temperature greater than 0 degrees Kelvin. 0 Kelvin. Electrons in the valence shell have enough energy to move into the conduction band. They might gain enough energy to jump into the conduction band, where they will become what? Free electrons and move freely as current when we apply a potential to that silicon crystal. As you can see in front of you, if we heat up that silicon crystal or we shine light on that silicon crystal, the electrons in the valence shell of each atom of the silicon crystal will gain enough energy so that it jumps out of that valence shell into the conduction band, where it becomes a free electron. And if we were to apply a potential, this electron will be driven in some direction. It will be pulled in some direction. You understand? So as you can see, in terms of energy, we have the valence shell. Here the electrons are at the valence shell energy level. And if they gain enough energy, they will move into the conduction band. I hope you get it, guys. Moving on. And when the electrons jump into the conduction band, they leave a hole and thus creating an electron hole pair. As you can see here, going back to that slide, we have this electron moving out of the valence shell and it leaves a hole. So after that, we now have an electron to hole pair. If this electron this electron, which is now in the conduction band, were to lose energy, how can it lose energy? Maybe we might decrease the temperature of the silicon atom, or we might stop heating the silicon crystal so that it cools down, and that electron will lose energy. And after losing energy, as I've already said, that electron can only exist in energy levels which are suited for its energy. Since the energy of the conduction band is very high than that of the valence shell, the electron is not suited for this energy after we cooled it, so it will move back to the other one, to the one it is suited to, which is the valence shell. As I've already said, if the electrons were to lose energy, it will jump back into the valence shell, recombining with a hole. This process is known as recombination. The key takeaway from this is that at any temperature greater than 0 Kelvin, the silicon crystal has some free electrons in the conduction band. They are very few. There are not a lot of them. They are few, but they exist for a silicon crystal which is above 0 Kelvin degrees Celsius. Moving on. Now, let's look at what happens when we apply a voltage across a silicon crystal which is at room temperature, meaning the temperature of that silicon crystal is above 0 Kelvin. So we are guaranteed that electrons do exist in the conduction band because they have enough energy to move into the conduction band. So if we were to apply a voltage across this silicon crystal, we assume this is our silicon crystal, we're only looking at atomic structure. So let me add some terminals. Here we apply a positive. Sorry guys, I don't know why. We apply a positive, and here we'll apply a negative volt. This will be the negative terminal, and this one will be the positive terminal. Assume we are applying a voltage across this silicon crystal. So what happens, guys, is that as soon as we apply a voltage to this silicon crystal, the electrons which are in the conduction band, as you can see, they are holes. They are holes in the valence shell. These holes represent where electrons are missing. There are vacancies, as you can see, spaces. So electrons do exist in the conduction band. So if we apply a voltage, the electrons will be driven or will be attracted to the positive terminal of the what? Of the voltage, or the positive terminal of the battery, assuming we have connected a battery across the silicon crystal. So they will be attracted to the positive what? To the positive terminal of the battery, where they will move into the copper and flow much more easily, because it's much more easier for electrons to flow in copper than in silicon. So some of the electrons will flow directly to the what? To the positive terminal, but some will flow from hole to hole, jump out of that hole, and then move to the other hole, jump out of the hole until they reach the positive terminal of the battery. The flow of electrons from hole to hole is known as hole current, whereas the other form of current flow is the direct flow of electrons from one place to another. That one is known as electron flow. But the one from the flow of electrons from hole to hole is known as hole current. You see, the electrons will move into that hole, jump out of that hole, move to the next hole, and then jump out of that hole again, move to the next neighboring hole. But some won't flow in this fashion. not all of them will flow in this fashion. Some will just flow directly to the positive terminal of the battery, whereas some flow from hole to hole. The whole flow of electron is known as whole electron flow, and the direct flow of electron through a substance is known as electron flow. I hope you get it, guys. Moving on. Most of everything here, I've already said it. When a voltage is applied, the electrons are attracted to the positive terminal of the battery. Only the electrons in the conduction band are the ones actually flowing. The other ones are contained within the atom. They are still attracted within the whole structure of the atom. Even though here, as you can see, I've shown the electrons. I've shown many electrons. Actually, in reality, the electrons are fewer than I've shown here. So guys, that's all from this lesson. I will see you in the next lesson. I hope you have enjoyed the video. Please, if you don't understand something, please write it down on the comment. Maybe I'll make another video and try to explain it better. And please don't forget to give this video a like and please subscribe. Thank you.